Okay, Math 352, we're back again. Today we're up to lecture 21, and we're almost finished with our topic of quadratic programming. And what we're going to do in this lecture, which will probably be quite a short one, is we're going to look at a few applications, okay? So a few areas in which we can solve problems by using quadratic programs. Okay, so we'll start with one that was actually quite familiar to us, and it's kind of nice to see the same problem occurring in a different context. So our first application is going to be least squares, strangely enough. Okay, now what does least squares have to do with quadratic programming? Well, let's see. Least squares can be cast basically as an unconstrained QP. How? So if you look at the least squares objective, what we're trying to do is to minimize over x the norm of ax minus b in the 2 norm. Okay, which is equivalent to minimizing the square of that. Oops. Right, so if we square our objective, so it's equivalent to minimizing ax minus b 2 norm squared. Okay, I mean, just like as we discussed a while ago when we were doing least squares. Okay, now that just equals ax minus b transpose, assuming we're working in a real space, ax minus b, which equals a half of 2 x transpose ax minus, let's just click all these terms together. So we're going to have a couple of a transpose b transposes x's. And the constant term will just be the b transpose b. Okay. A transpose A, as you should have discovered in tutorials, is positive definite if it's full rank, or if it's not, it's positive semi-definite. So what we basically have is a quadratic function in X with a positive definite matrix. So it has a minimizer satisfying. Well, let's look at the equations. Remember, you find the minimum by negative p inverse q for a quadratic, so it's going to be A transpose A to A transpose AX equals negative q, which is going to be 2A transpose B. And if we just get rid of those factors of 2, which we don't need, we're back to our normal equations. Okay, so this is another way to derive the normal equations for these squares. So the normal equations are simply the minimizer of a positive definite quadratic function. Okay, the normal equations as we've seen. Okay, so I guess this is not so much an application as it's an illustration of tying together some concepts in this course. Okay, solution, and as we know, we can solve the normal equations. Now, what we hadn't talked about previously that we can do now, when you actually solve the normal equations, because I think we haven't talked about this before, when you solve the normal equations, you've got a positive definite matrix, A transpose AX equals A transpose B. Just remember, when you actually solve these in practice, because this is positive definite, you solve this system by Cholesky factorization. Okay, so the standard normal equations method for solving the least squares problem is by computing Cholesky factors of A transpose A. So solve by, just in case I haven't said this before, solve by computing Cholesky factors of A transpose A, and in fact we did this in a computer class a couple of weeks ago. Okay, so to do it this way, you form A transpose A, you compute the Cholesky factorization, which is what MATLAB will do automatically if you use backslash, and that gives you a solution. Note once more that, however, the normal equations are not a well-conditioned way of solving least squares problem. You're much better off to use the QR factorization. Okay, so that's our first little topic. Second one is one from finance. So stock portfolios. Okay, so now we're going to put on our investor hats, and we've got some money to spend, basically investing in shares of various companies. So let's just set up a few variables here. Let xi be amount of money purchasing shares in company I. Oops. So we've got a certain amount of money to spend. We have some number of companies, in companies to possibly invest in, and each company has an expected return per dollar of shares in company I. Okay, what else do we need to know? We've got M, total amount of money to invest, and we'll need, basically we have a certain amount of return that we want to get, so desired return per dollar. So we want to basically get a certain interest rate or a certain amount of return for each dollar we invest. Okay, now so far there's nothing to stop us just investing in the company that that has the highest return. So there's a little bit of it has to be a kind of a flip side here. So let theta ij be the covariance between $1 invested in share I and $1 invested in share J. Okay, so this is kind of a measure of how much the performance of these two companies, companies I and company J, are linked. Okay, so if basically company I crashes and their stocks plunge by a whole lot, will the same thing happen to company J, or is company J pretty much independent of company I? And we measure this by the covariance. Now, this is not a course in statistics, so we're not really going to go into any details there, but it's just a kind of a measure of how much two companies are linked. Because, of course, whenever we're investing, this is a kind of stochastic problem. We don't actually know how companies are going to perform. We can guess. We've got a kind of a mean guess of an expected value of return, but there's a certain amount of variance and risk involved in each investment. So it's good if when you're investing to kind of invest in a number of different companies whose performance doesn't kind of vary together much, so they're not correlated or there's zero covariance. Okay, so let theta, capital theta, in case you haven't come across that symbol before, is the covariance matrix. With elements. So it's just a collection of all these theta ij's. Okay, so what we want to do, we're not trying to maximize our return, we're trying to achieve it with minimum risk. So we're not being greedy and trying to get as much money as we can. We're trying to guarantee that we'll get our desired amount of return with minimum risk. Okay, so the QP is, so it turns out that what we want to minimize is this quantity here. And those of you who are studying finance will understand this quite well. Those of you who aren't, just look at it as kind of cultural enrichment. So I want to minimize basically this quadratic involving our covariance matrix. So if we're investing in shares that don't vary together, we're going to have older zeros or very small numbers in here, and this will be a small quantity. Okay, subject 2. Now we're just going to make sure we get all the constraints. First one, our vector of x's has got to be greater than or equal to 0. We can't invest negative money, they're not going to pay us. Okay, what else do we need? Okay, the amount we invest, sorry, the expected return over all our investments has got to be greater than or equal to our desired return times the amount of money we have to invest. And finally, don't forget, if I write capital 1 like this, it's just a vector of 1s. The sum of all the x's, so I could just write that as a sum if I wanted to, is equal to the amount of money we had to invest. Okay, now I think that's all we need. So you can see that we can pose this investment problem as a QP, and we can solve it on our computer and then go and invest away, knowing that we've done the safest thing we possibly could, subject to the data we've got available. Okay, so there's our finance example. We're going to have another kind of economically motivated one next. So remember when we started linear programming, we looked at a problem about producing chairs and tables. And we had a few kind of unrealistic assumptions built into that model. So this time we're going to go for the new and improved QP version. So we're going to go back to our, if you remember, the Brown & Co. furniture shop. There it goes. Okay, so what we produce, firm produces X1 tables and X2 chairs per week. And we have that material, labor, and profit are as follows. Okay, so just draw up a table of some various constraints we've got. So we have wood, labor, and profit here. And we'll have table, chair, and supply per week. Right, so basically a table requires 3 bits of wood, 3 units of wood, requires 4 units of labor, and the profit we get per table is 4 minus 10 to the minus 3 x1. Okay, I'll talk about what these terms mean in a moment. A chair only takes 1 piece of wood, still fairly labor intensive, takes 3 units of labor, and the profit per chair is 2 minus 10 to the negative 4 x2. Like I said, I'll explain these terms in a moment. And each week we've got a certain amount of supply available to us, 200 pieces of wood and 480 pieces of labor. Okay, 480 man hours or whatever of labor. Okay, the two linear terms, oops. Let's see if I can write linear correctly. And the profits reflect the fact that the firm now is large enough to affect prices, basically, through over or undersupplying the market. So basically, if our firm goes and makes, well, 1,000 tables, or heaps and heaps of tables, then the profit per table goes down because there are so many tables on the market that people are unwilling to pay such a high price for them. So in our linear programming example of this problem, we assumed that our company was small enough that the number of tables and chairs it makes doesn't really influence the supply and the demand and the prices in the market. This time we're a bigger company, and the more we produce, the lower the prices that we're going to get for them are going to be. So this is a more realistic situation, and we'll see that when we try and maximize profit, we'll now get a QP. So we want to maximize profit or minimize negative profit. So our QP is minimize over x. So the profit per chair is 4 minus 10 to the negative 3 x1 times the number of chairs and its minimum. Okay, and we're going to have the same kind of thing for the tables, for the chairs. Let's get it the right way around. x2, 2 minus 10 to the negative 4, x2. Now just write that out in a more conventional way. So if we expand all these out, we're going to get 10 to the negative 3 x1 squared plus 10 to the negative 4 x2 squared minus 4x1 minus 2x2. See, now we've got a quadratic to minimize, not just a linear objective, subject to the same kind of constraints as we had in our previous problem, our previous production problem. Basically, that the number of chairs and tables we make is limited by our amount of wood, and by the amount of labour that we've got available to us. Okay, and we can just use our active set QP method, or some other way, of solving this optimization problem to work out how many tables and chairs we should make in order to maximize our profits. Okay, now I've got one more example to look at, and then we're going to call this lecture finished. So, our final example is a pipeline problem. Just to sort of change flavour a bit. So what we've got here, water flows through a network of pipes. Okay, the network of pipes looks like this. So let's draw ourselves a wee sketch. Okay, so we've got basically some flow coming in, then we've got some pipes, some flow coming out, and we've got a couple of extra pipes. So you can think of this as a layout of pipes in a city or something. A network of blood vessels. For whatever reason, this is our system of pipes that we're interested in solving for the flow. Okay, and let's say we've got an inflow of 100 and an outflow of 100. Okay, so that'll be liters per minute or whatever. You can, if you want to, you can attach some units to that. And we'll label the various flows: x1, x2, call this one x3 up here, x4 here, x5 and x6. And x6 has a one-way valve. Okay, so I'm just going to draw that as an electrical diode. So basically, flow can only go through the pipe with x6 in it in one direction only. Okay, so this makes this different from your average circuit problem. We've got a few physical things we need to talk about briefly. Once again, if you're not particularly interested in this application, just look at it from a kind of mathematical, interesting point of view rather than worrying about understanding the physics of it. So the flows are laminar, so that the pressure drop we'll call it delta Pi along pipe I is proportional to the flow rate. Xi. Okay, so you've got some kind of resistance like pressure drop equals some kind of resistance times the flow. Okay, this is exactly like Ohm's law for electrical circuits, where you've got a voltage drop is equal to a resistance times a current. So under certain conditions, fluid flow behaves in a very similar way. Okay, the flow that occurs minimizes the energy loss in the network. Okay, and also pipe 6 has a one-way valve. Now, note that it doesn't actually matter which direction I stick the arrows on these pipes. They just indicate that if I get a positive number, say for x1, it means there's a positive flow in the direction of my arrow. I could equally well get a negative number for x1, which would tell me that there was flow occurring opposite the direction in which I've drawn the arrow. The direction of the arrows is completely arbitrary, although it makes some kind of physical sense of my picture here. Okay, so what is the energy loss? Well, basically given by this expression here. The amount of power being used, or energy being lost, is given by the sum of the resistances times the flows squared. This is like your I squared R losses for those electrical engineers out there. Okay, and our constraints are basically that at these junctions here, the inflows and the outflows match. Okay, so we've just got a conservation equations. So at the inflow junction, we've got 100 coming in. So x1 plus x2 must equal 100. No flows going anywhere else. We'll call this junction 1, and this one junction 2. At junction 1, if we just equate the inflows and the outflows, we've got x1, x5 and x6 coming in. x6, sorry, equals whatever's going out, x3. And likewise at junction 2, we've got x2 coming in only. And that equals, so just label these, and that equals x5, x6, and x4 added together. That's my conservation equation for junction 2. Now, I've got my outflow condition, which is x3 and x4. And the thing that makes this interesting, that requires us to sort of use these QP techniques here, because otherwise you could just solve this like a normal network of resistors, is this one-way valve. x6 is greater than or equal to 0. That kind of constraint is more difficult to incorporate in the way you might be used to solving electrical circuit flows, or these kind of fluid flow problems. So that's why we actually need to use our QP algorithm for it. Okay, so here we've got a quadratic objective, we've got a number of equality constraints, and our problem has also introduced some inequality constraints. Okay, so this allows us to attack a kind of wider range of possible problems here. Okay, so I guess that's the end of this application and about the end of the lecture. In the last lecture for the course, which is tomorrow's one, we're going to look at how we can use our ideas from quadratic programming in the more general context of solving general nonlinear optimization problems. Okay, so we'll come back to that tomorrow, but until then, I will see you later.